Hello friends, welcome back. I am Rajneesh and today in this session we are going to understand some basics related to the memory management. To demonstrate this we are going to use an Ubuntu machine. So how does the memory management works in a Linux kernel? The operating system or the memory management unit of the operating system makes use of virtual memory. Why virtual memory? There could be a situation when you have a set of processes that require more than physical RAM, that requires more memory than what we have in physical RAM. For example, I have 4 GB of RAM and there are a set of applications that require 10 GB to run. They require 10 GB doesn't actually mean that they will be using 10 GB of RAM. They might be using 2 or 3 GB of RAM and even more than 4 GB of RAM. So there should be something that makes operating system understand the memory that is even more than RAM. So that led to the approach of virtual memory. So virtual memory, the size of the virtual memory is too much as compared to the size of RAM. In case you have 4 GB of RAM, you may have virtual memory or virtual address space that could be 10, 20 GB or even more. So what happens? The main objective is we can run the applications the size of which is more than the actual physical memory size. We have 4 GB of RAM, we can run the applications that may require around 10 GB of memory. So how does it handles? How does the operating system handles it? Virtual memory is divided into pages. The size of the page is defined at the time when the kernel is compiled. By default, you will see it as 4 kibibytes, which is 4096 bytes. The physical memory is divided into frames. So what happens? There is a process that tries to access or asks the memory management module, yes, give me 4 GB of memory. The memory management unit of the operating system allocates the pages that contribute to around 4 GB of memory. Okay, so it will get the set of pages that combinedly will be equal to 4 GB of virtual memory. But these pages are not yet mapped to the frames, because as soon as they are mapped to the frames, that amount of RAM will be utilized. For example, if we are talking about the same scenario, application access or asks for 4 GB of RAM, and at the same time if it maps 4 GB to the RAM, that will completely be filled up. So what happens is the application asks for 4 GB, 4 GB virtual memory is allocated to it. When the application tries to populate data in these pages will be mapped to the frame. However amount of data is put into it, the same amount of frames will be used. Got it? And the mapping is managed in page tables. Okay, maybe you are not pretty clear, so let's have an example in lab. Let me open two terminals. How does kernel manages or keep tracks of the memory? There is a file proc meminfo. Here you can see all the details about total memory which is visible to memory management unit, total amount of RAM which is free, memory used as buffers, cached, and complete details. Okay, so I would like to monitor a few things, so I'll put a watch -n, delay is going to be 0.1 second, cat proc meminfo and grep minus I commit free minus m. So free minus m is going to show you the utilization of memory. How much is the total RAM which is visible to the memory management unit? How much of RAM is used and how much of RAM is free? How much of the swap you have, how much of swap is free? Commit limit is utilized. Okay. Okay, if we talk about the kernel or the Linux kernel, it has the ability that it can overcommit memory. Means we have 4 GB of RAM, it can overcommit the memory to the applications that they may use even more than 10 GB of memory. That's overcommitting. With this, we have two variables which are associated. One is overcommit memory, which has three values, 0, 1 or 2. Value 0 says overcommit on the basis of heuristics. In case the application is asking for the memory which is more than what we have in RAM, you may allocate that process that amount of memory in case that looks fine to you on the heuristics basis. For example, an application tries to access 100 GB, of course that is going to be too much, so just deny access to that. But in case it's trying to access a few GBs, yes, assign it to that. Then there is second option 1, which says always overcommit. An application asking for 200 gigs, allocate to it, because we are allocating the virtual memory. The physical memory will be used only on demand, but yes, there could be a situation when you get out of RAM because you have allocated too much amount of RAM to a process. Third option is overcommit, but only on the basis of certain situations or on the basis of overcommit ratio. If you would like to see the details about it, user share doc Linux doc VM, maybe in sysctl, or let me just see where it is. Overcommit accounting. So here you can see that it has three values. 0, heuristic overcommit handling. Second is always overcommit, whatever amount of memory it requires, yes, allocate it. Second says don't overcommit. The amount of memory that you are going to allocate to a process, or the amount of memory that an operating system can use, is swap plus some percentage of RAM. So here you can see swap plus some percentage of RAM. By default that is 50%. So this will be applicable or available to the complete operating system. Okay, so coming on to committed address space. So this is what your commit limit is. So here you can see the current overcommit limit and amount committed are variable in committed address space. Committed address space means the amount of memory or the virtual memory presently requested by the operating systems or various applications present inside the operating system, and commit limit is the maximum limit that can be allocated to various processes in the operating system. Okay, so moving on to an example. I have certain programs that will make use of virtual memory or the physical memory too. So right now I am going to use eat memory virtual, that is going to utilize certain virtual memory that I'll specify, for example 4096. So what is going to happen is this application is going to use around 4 GB of virtual memory. We have nearly 3.5 gigs of physical RAM available, so it should start making use of swap in case I am using physical memory of 4 GB, but not. I am only utilizing virtual memory. So what will happen is committed address space, or which actually means the amount of virtual memory allocated to certain processes is going to increase. Right now you can see that the value is fluctuating, but it's nearly 5.7 GB. So I run this process and here you see it increased by 4 GB, but if you look at your physical RAM, it was not increased by too much. The reason being it consumed only virtual memory. I'll run one more instance of it and you can see, you can have a look at this one. Now it should go to nearly 13. So here you see 10 plus 4, nearly 14 GB of RAM. So what it says is, in case you want to run your operating system in a stable state, you should have nearly 14 GB of RAM present on it, because you have a set of applications that are utilizing nearly 14 GB of virtual memory. So here it again increased to 18 GB because I added 4 more GBs to virtual mem. So right now you can see that the set of applications that I have in the operating system want 18 GB, but they are still running. Instead I have just 4 GB of RAM. In other words, I have 4 GB of RAM, but I am running the applications that need around 18 GB of memory. So that's what is overcommitting, and that's what is virtual memory allocation. Okay, I would like to show you one more thing. PSAX to show all processes, and O is to specify certain options that you want to specify, because I would like to have a look into the selective fields: RSS, resident set size, or the actual RAM utilized by a process; VSZ, virtual size, or the amount of virtual memory used by an application; and COM stand for command. And I am going to grab, first of all, let me show you. So this makes sure that this is your actual RAM used by some process. Right now it's in it as a first, so let's forget about it. This is the virtual memory required by that process, and this is the name of the command. So now I am going to grab each mem out of it, and here I see that each process, this is in kilobytes. So kilobyte, this comes out to be around 4 GB of virtual memory is utilized by every eat mem word process. And if we talk about the actual memory utilization of these processes, this is actually utilizing only 352 kilobytes or kibibytes of memory into 3 for the 3 processes. Okay, so this is the way you can see certain selected parameters associated with a particular command or associated with that particular process. Okay, so that completes the virtual memory part. The second part that we are going to understand is the actual physical memory allocation. Before that, I would like to kill these processes. So as soon as I killed them, it reduced from 18 to nearly 5.7. So right now the virtual memory allocation is around 5.7 gigabytes. So now I have one more process, which is eatmem, which is going to actually eat the physical memory with that amount of size. So I am going to run eatmem with 100 megs. I'm not using too much, because in case I would be using 4 GB, it will make my PC reach to the hung state. So I just tried to allocate 100 megs, and let me see, minus EF or AXO. I would like to see RSS, VSZ and command, and I would grab eat out of it. And here I can see that this is a process which is running in background, and if you see, it's utilizing nearly 100 megs of nearly 100 megs of virtual memory and nearly 98 megs, nearly the same amount of physical RAM or RSS is utilized by this process. Okay, did you have a look into this one? If not, you can have a look into this one once again. Right now it's nearly 284 megs of RAM which is free, and I'm going to run one more instance, and that should come out to be nearly 187. So here you see, okay, let me see. Okay, let me just call them again. Kill all. Okay, so as soon as I just killed these two processes, you can say that you got nearly 200 megs of RAM which was freed up. So 285 become 477. Just to call them once again, here you see 100 megs is reduced from the free RAM. Have a look into it once again, and you see it reduces by nearly 100 megs. So what is happening is, if you are talking about the actual physical allocation of the memory that actually uses the RAM, and other is, so in this eatmem, what it actually is happening, it is asking for 100 megs and then filling that 100 megs with some part of data, which makes you reach to the same situation where you are actually using 100 megs or 100 megabytes of the actual memory. Okay, let me free it up. Okay, so it's all freed up. So this is what is physical and virtual memory. Okay, other thing you might be confused about, from where or how do we find out a page size? You just type the command getConf -a to get all the parameters and grep -i page, and here you see that your page size is 4096 bytes, which come out to be 4.9 kibibytes. Okay, and the size of page frame is always the same as the size of page. Moving on to the next slide now, page frames. So as we just had a look into it, your physical memory is divided into frames. Pages, your virtual memory is divided into pages, and physical memory is divided into frames. So whenever you need to fill something in the memory, or whenever the application tries to use something, it just puts the page into the frame, and the mapping is managed by page table. Memory management unit translates this this virtual memory into physical memory addresses using page map table. Translation look aside buffer. If you talk about page map table, the size or the access takes more time, it's more time consuming. So page, what it does is it keeps a cache of the page table that is closer to the CPU, because the page tables lookups are actually costly. So there is a TLB cache or translation look aside buffer which is close to the processor, so that it can have a look into that mapping, and in case it's not able to find that mapping in TLB cache, then it will try to fetch it from the actual page cache. So to improve the performance and make a fast lookup, TLB cache is used. So any virtual to physical memory address translation first checked in translation look aside buffer. If it's not found, TLB miss will happen and MMU will ask page table for the translation, and it will fill up that details, or the TLB cache will be filled up with that mapping. Huge TLB. If we talk about the applications that require huge amount of memory, for example, if I have an application that makes use of 4 GB of memory, so how much pages will we have? Okay, so if I have an application which is using 4 GB, which means 4096 megabytes into 1024, so this much of kilobytes divided by 4. So what is going to happen is it will have nearly 10,48,576, nearly 1 million entries. The same program is having nearly 1 million of page map entries to map to the actual physical address. So what other part can be done to reduce the number of entries in the page tables? Kernel has a support for HugePages. Cat proc meminfo grep -I huge. So here you see that you have a support for HugePages of size nearly 2 megs. So by default the page size is only 4 kilobytes, but if you have some applications that need to be specifically making use of huge page size, that application make use of huge pages, so you have less number of page entries, and the access to the RAM or access to the memory is going to be pretty fast. Because if you talk about the situation where you have the huge page size is 2 megs, so the number of entries is just going to be nearly 2000 in comparison to 1 lakh page entries or page table entries when we were using the page size of 4K. So that's the reason we make use of huge pages. I'll show you an example. Okay, examples we'll see in the later session because this session is already big one. Okay, so this is huge TLB. Page size is 4K by default. Hardware supports huge page size like 2M that I just show you. Large page size reduces the number of page table entries and make fast access. Huge TLB feature in kernel support large page size. Okay, then there are some calculations associated with memory. Buffer plus cache, they are also known as page cache or disk cache. So this is the memory which is currently allocated to hold file which are backed by files, or this is the amount of memory which is backed by the files. So this memory, for example, if I am talking about a file which is around 2 GB in size and we try to read that 2 GB is loaded into the cache and the metadata information is loaded into the buffer for the same. File backed by file or backed by storage simply means that the file exists at the backend in some storage. Buffer, they contains inode, directory entries, superblocks, or result from direct IO. Cache, actual contents of the files that we are opening or accessing. Active plus inactive. So this is the total amount of memory which is under the control of page replacement. Memory management unit of the operating system should know which pages are actively being used and which pages have not been used in the recent past. The reason is we need to free up the pages so that more applications can be allowed access to it. So total memory under the control of page replacement algorithm. What it includes anonymous pages. Anonymous pages are the pages that are not backed by the storage. For example, applications might be doing some kind of calculations. For example, if we are talking about database calculations that are happening only over the RAM, you are trying to fetch hundreds of entries, so it fetches out through a select statement hundreds of entries, but they don't have any file at the back end, so they are all cached or received as anonymous pages. So active plus inactive, there could be anonymous, active anonymous pages, inactive anonymous pages, buffer and cache, and swap cache. Swap cache is a memory that was swapped out once. Why? It was swapped out because we were having crunch of memory and the processes were waiting for the memory to be allocated to them, and these were using anonymous pages which are not backed by the storage. So we cannot just flush them to the storage. The option was to swap them out to the cache, and that page was again required by the application, or this set of pages were again required by the application, and they were fetched back to the RAM. So now swap cache is something which is present in cache, which is present in swap, as well as which is present in memory. So this is the duplicate entry. So in case the page replacement algorithm has to remove the memory out of it, it's not required to be swapped out again. Anonymous pages are the pages, anonymous pages are paged out to the swap area. Anonymous pages are paged out to the swap area in tight memory situation. So what happens if you are talking about anonymous pages? They don't have disk at the back end, so they need to be swapped out to the swap. Page cache consists of non-anonymous pages are flushed back to the disk in tight memory condition. One more thing that you are required to understand is kernel space and user space. If you are talking about memory, it's divided into two parts. One is the kernel space, other is the user space. Kernel space means the space or the location in the memory on which the kernel is executed or the kernel is present, and it takes care of the functions or system calls. User space is the memory space where user programs run. Kernel space where kernel executes and provides its services. Now, the kernel has the ability to access the user space whenever it requires. So it has access to kernel space as well as user space. If you are talking about user space, it has access only to the user space. It cannot go into kernel space. If it wants to have interaction with the kernel, it makes use of system calls, and then it can access something in kernel space. So user space where the user program run, a user process can ask kernel space about anything that it needs to know in terms of system calls. Now, this is also an important diagram that we need to understand, because we just had a talk about translation look aside buffer. So this is a TLB cache which is very close to the processor and which keeps track of page map tables which are recently used. So page map table or page table simply means it has entries that map a page to a frame. That is, it converts a virtual address into a physical address. A process says I want to access page number X. TLB cache is going to convert it into frame number 5 which an application can access, and it will be satisfied for it in case TLB cache hits. In case it makes a miss and the entry is not present in it, so we need to go to page table, and in page table it is going to see the mapping for the virtual address to that physical address. In case the hit is found, means an entry is found, we know where is the physical page that we are required to access, and at the same time the same entry will be fetched from the page table and it will be brought to TLB cache. So now TLB cache knows about this new entry, and the next time the application will try to access it, it will find an entry in TLB cache, and the access is going to be too fast because we will not be required to go to page table entry. Okay, there could be a situation in which page table entry also is not present. Why? Because this virtual address was never mapped to a physical address. It's trying to access something which is not yet mapped. Either you have not get data from the disk, that could be the one reason. So what it does is it tries to fetch it from the disk and adds it to this page table entry. So what happens is, now if it has an entry in page table, it's fine. If it doesn't have an entry, a mapping will be created for it from the disk, and now this mapping will be present in page table as well as it will be present in the TLB cache. So now if the same process tries to access the entry that was accessed last time, the access is going to be pretty fast. One more thing that you need to understand is the life of a page. Page, as you know, is present in virtual memory, and frame is something which is present in your RAM. Now, one page, either it could be free, it could be active. So first thing, the frame is completely free. It doesn't have anything inside it. Once it's allocated, or once the page is allocated, it has some data in it and it becomes active. Now the active page, in case it's recently accessed, it again becomes active. And okay, first let's try to define all this. Free page means the page is not mapped to anything, it's completely free and it's ready to be mapped to anything. Page is active means it was used in very recent past. It makes use of least recently used algorithm to fetch out which is actively used. So active means it was very recently used. Inactive, it could be inactive dirty, inactive laundry, or inactive clean. Now inactive dirty means the page is inactive, it was not used in very recent past, but there are some modification in the page that are still to be written to the disk. Okay, so there are still some modifications in this page, they are still to be flushed to the disk. After, now if this page is paged out, it becomes active laundry, means it's now in a process where it is trying to flush the modifications to the disk, and after all the modifications for the page have been flushed to the disk, it reaches to the state of inactive clean. In the meantime, when it is trying to flush the modifications to the disk, in case the page was accessed again, it will become active, and in case it was not accessed during the time when it was flushing the details to the disk, it will become inactive clean. So inactive clean means this page is free and is not required any kind of swapping, it can just be freed up to be converted into free page so that it can be allocated again. Page could be free, completely free, can be accessed or allocated anytime. Inactive clean, page is not recently used and page doesn't have any modifications that are yet to be flushed to the disk. So in case of crunch of memory, it can be cleaned up and it can be converted or deallocated to become a free page. Dirty, it has some modifications that are yet to be flushed to the disk. Laundry, the modifications being flushed to the disk. Now here is the structure of the RAM. Now in this laptop I have nearly 4 GB of RAM. It should be 4096 MB of RAM, but if I look into the output of free -m, I would see that's nearly 3.5 GB of RAM. So where is all the RAM gone? Okay, okay, so total RAM is 4 GB, but I cannot see 4 GB because there is some RAM used by some reserved bits and some binary code which are not accessible to the memory management module of the operating system. So if we are talking about blue color, That's the total mem total, or the total amount of RAM, usable RAM, or the RAM which is available to the memory management unit of the operating system. So the memory management unit can deallocate or allocate memory out of it. Okay. So if you talk about this total mem total variable, you have some part which is free, which is not yet mapped to anything, which is readily available in case a new process comes and asks for memory that's allocated from the virtual memory, and in case that's trying to access or modify some data, tries to access big files, that can be allocated frames, or the pages can be mapped to the frames because we have free memory available. Now the memory that is used is now displayed in, so it's in red color, active plus inactive memory, which is available for page replacement algorithm that makes use of it to allocate and deallocate memory. So this is displayed in red color. It has two parts, active and inactive. Active memory, which was used in very recent past, inactive, which was not used in the recent past. Now active could be anonymous, that is, which is not backed by the storage or the file. What word did I use? So it could be anonymous or it could be non-anonymous. Anonymous means it's not backed by the file storage, and non-anonymous is the one which is backed, or which is memory mapped, which is backed by some file in the hard disk. So if we talk about buffers and cache, buffers, some metadata information, superblocks, and inode details related to the files being accessed from the hard disk, and cached is the actual content which is being cached from the hard disk. So together they are joined to become page cache or disk cache. This is the non-anonymous memory. Now we come on to anonymous memory. Anonymous memory has one part which is swap cached. Swap cached, it means some amount of anonymous memory which was swapped out. As you all know that swap space is present in the hard disk. So for example, this was around 512 megs of RAM or 512 megs of memory, which was swapped out because there was crunch of memory. So now the application again required the RAM and again required to access this application, and that part was swapped in back from the hard disk to the memory. So now you have duplicacy of the data. In case the same part which is swap cached is required to be cleaned up by the page replacement algorithm, or is required to be flushed off, we need to free up memory from it. We are not required to swap it out again, and we save some IOs and it becomes faster. So page replacement algorithm keeps track of it, and the total is, this part is anonymous memory. Anonymous, which is not backed by the storage or not backed by any file. For example, as I gave you earlier, MySQL query is getting thousands of records, so they are actually not stored in the file, so they are present in RAM itself as anonymous memory. So understanding various parameters that we had a look into by typing the command proc meminfo. Mem total is the total amount of RAM which is visible to memory management unit. Okay, it is actually the total amount of RAM minus some part which is used by the kernel and some reserved bits. it shows the size of your physical memory that is mappable by the kernel. Okay, memory free, which is free and which is not allocated for any purpose, which is assigned for nothing. Buffers, temporary storage for raw disk blocks, as we discussed, metadata information, superblock information, inode information related to the file. This is basically used by the application that makes use of files or something, the files which are present in the disk. Cached, the actual content of the file which is required by the application. Swap cached, as I already discussed, this is anonymous memory which was once swapped out is again swapped back in. So in case we need to swap it out again, it's not required to be done, and we save some time, save some IOs. Active, recently used, cannot be reclaimed unless absolutely necessary, because it is actively used, it was used very recently, so operating system or memory management module knows that it may be accessed in near future. So until and unless it's compulsion, it will not free up any kind of RAM or any kind of pages which are active. Inactive, that are not recently used. Active, anonymous, these are the pages that were used in very recent. Anonymous means they are not backed by the file. Some like of example, some MySQL queries, output of some MySQL queries. Inactive, inactive file, inactive anonymous, the amount pages that were used but not in very recent past. If required, they can be freed up. They are not backed by the files. Active, file based, which are backed by files. Inactive, not recently used, backed by disk or file. Unevictable, these are the pages which cannot be paged out at all in any reasons. Locked, so locked, this is the size in kilobyte of the memory for which the memory is locked, and this memory cannot be freed up. So enable its privileged programs to lock memory segment into physical RAM, the amount of allocated memory that's strictly prohibited from being swapped out. So unevictable is one part which cannot be paged out. Other is blocked, which cannot be paged out because it's locked. Okay, swap total amounts of swap available. Swap free, total amount of swap which is free, which is not used for anything. Dirty, the amount of memory or the amount of pages that have been modified since they were last accessed. For example, I opened a file in VI editor or any other editor, any log file which the application opened and modified something in it, that becomes dirty. So means the file is still to be flushed to the disk. Means there is some difference between the actual file and the file which is present in the page. Write back, this is the amount of memory that is presently being written to the disk or swap. Anonymous pages, they are not backed by the file. Mapped, total amount of file contents which have been mapped inside a process address space. For example, if we are talking about the libraries, they have been loaded and they need some amount of RAM, so this is the actual amount of memory which has been utilized by a processor. by a process. Uh, the amount of memory that a process asks is virtual memory. Mapped is the actual memory that is utilized by that process, or that is mapped. For example, the libraries that have been loaded by this process. Shared memory between the applications. Slab. In kernel data structure cache. Pages used by the kernel memory pool slab allocator. So because the kernel keeps track of the pages, there is some kind of data structure information that it requires to keep track of the pages. So there is some cache which is present in the kernel. That is the cache related to the data structures in the kernel. Slabs reclaimable. The part of slab that might be reclaimable or that might be freed up. S slab, the part of slab that cannot be reclaimed on memory pressure. Even in case the memory is not available, it cannot be reclaimed. Kernel stack. So let's talk about the stack. Stack means the amount of memory that is available with the program, which we can use to provide it the parameter and receive the output of that particular program. Application stack is where the parameter values and the return addresses are pushed among the other needs. So what happens when the same application moves to the kernel mode? When the same application enters the kernel mode by means of system calls, this user space stack is not used. Here kernel mode stack replaces the role of user space stack. So an application, for example, we are passing 10 arguments to it, 10 specific files to it, so that it can take care of that. So these 5 files that we provide, and in case we want the output in sorted format, so the total amount of memory used by passing these files and getting the output of these files is going to be known as stack. But if the same case happens when we are interacting with the kernel through system calls, that is going to be known as kernel stack. Page tables. So page table is actually a data structure that we had a talk about in the previous session also. It simply maps your pages in the virtual memory to the frames in the physical memory. It's a data structure that helps a hardware structure called memory management unit to translate virtual addresses to physical addresses. This is the basis of protected mode, where each task is given a different process address space, and one process cannot get into the address space of other process. Therefore each of them feels like they have its own set of RAM visible to itself, and that's actually the virtual memory that is visible to it. Memory used by the kernel to hold hardware page tables, that is visible over here. NFS unstable. If we are talking about an NFS server, it could be a situation when NFS server has received the updates, but they are not yet flushed to the stable storage or the disk. So this is what is present in NFS underscore unstable variable in kilobytes in proc meminfo. All these variables that we are talking about are present in proc meminfo. Bounce. So this is the memory used for block device bounce buffers. Bounce buffers are actually the buffers that are used by some devices that are required. For example, let's talk about some of the devices that do direct memory access. They don't have the capability to access the memory which is more than 1 GB. So what happens is they make use of okay, let's talk about write back TMT first. This is a memory which is used by Fuse file system for temporary write back buffers. So when we are actually writing to the file system, they are first written to the write back TMP. Commit limit. This basically use of overcommit ratio. When the value is set to 2, it's utilized. So this is the maximum limit of virtual memory that can be allocated to the operating system. It comes out to be overcommit ratio star physical RAM plus swap. Committed address space, the amount of memory that is presently, the amount of virtual memory that is presently have been allocated on this OS. VM alloc total, the total size of VM alloc memory area, the amount of VM alloc that is used, and this is the largest contiguous block of VM alloc area which is free and can be used. Hardware corrupted, so no hardware is corrupted, it will display 0. Anonymous HugePages, so we just had a discussion about HugePages. In case there is an application that tries to access a huge amount of memory, that application can be written in such a way that it understands or it tries to access the HugePages. So it will help us to reduce the size of the page table. The size of the page table is less, means the access is going to be faster because we need to scan less number of entries. So this is the total number of anonymous HugePages used, total number of HugePages available, number of HugePages that are free, number of HugePages that are reserved. An application asks for HugePages, it's allocated that number of HugePages. So first of all, they are reserved for it. As soon as that application starts using it, they are allocated to the application. The number of HugePages for which a commitment has been made to allocate from a pool, but allocation is not yet done, they come under reserved. I'll show you an example. HugePages surplus, these are the additional or the overcommitment of the HugePages, the number of HugePages in the pool above the value of NR HugePages. The maximum number of surplus HugePages is controlled by overcommit HugePages. So there is a variable overcommit nr underscore overcommit underscore HugePages in sysctl parameter, which specifies how many surplus pages can be allocated. Huge page size that we just had a look into it was 2M. This is the size of huge page that kernel supports, and direct map 4K and 2M. As we just had a talk about, the default size of page is, or the page size is 4K. So the total amount of memory that has been mapped with 4K pages is around 77 MB, and the total amount of memory that has been mapped for 2 megs of pages is around 3.7 GB. So direct map 2M means the huge pages, the memory used by the huge pages, or maybe used by the huge pages. Okay, so I would like to show you a demo of huge pages also. Let me open one more session. So here you see the huge pages, the total number of huge pages in proc meminfo. Okay, I would like to show you here proc meminfo. Here are these variables that we were just discussing about. So they all are present in proc meminfo. Coming back to this location, here we can see that the size of huge page is 2 megs. I have an application which is going to allocate huge pages, gcc -o hugepages.c. Okay, so what it is going to do is hugepages.c, it's going to allocate around 8 megs of huge pages, and the size of huge page is 2 megs. So in other words, you can say it's going to allocate itself 4 huge pages, right, of 2 megs each. That's going to count for 8 megs. So I just run the command huge pages. It cannot allocate memory. The reason being, we don't have huge pages available. So I need to make it available. sysctl -a grep -I huge. So the number of huge pages that I need to support is, we can have it in any numbers, but at least it should be more than 4, because 4 will be used by this application. In case you want to keep it consistent after the reboot, I can just add them to the end of /etc sysctl.conf. Let's say I am going to provide or allocate 10 huge pages. So now 10 huge pages will be available after the system has been rebooted, or just to reload sysctl.conf, I am going to run sysctl -p. So here you can see that the total number of huge pages has now been increased from 0 to 10, and all of them are free. Okay, now I am going to run the script huge pages again, and here we can see that as soon as I ran it, it initiated and asked for 4 huge pages or 8 megabytes of huge pages. So here you can see that proc meminfo says 4 huge pages are now reserved for this application. As soon as it will start writing, now huge pages free are 6. So where are these 4 huge pages gone? They are presently being used by this application, huge pages. So now there is nothing reserved for anything, because 4 huge pages or 8 MB of huge pages that were allocated to huge pages application are being used. Now press any key to read from this memory area, and here it tried to read the details from this huge memory area, and it was able to read it successfully. So after it has read the details from it, it has released or freed up the huge pages that it used. So here you can see that you have the huge pages which are again free. So what was the benefit? The page table entries, the number of page table entries are reduced a lot. The access is going to be pretty fast. So that's all for today. I hope I was able to make you understand these things. Thanks for viewing the video. Have a great day.